Now I'd like to talk about our Riemann sums and consider when we know we have an overestimate versus an underestimate and with regards to approximating the true area under our curve. So again, we're in the general context that I have some function f of x. I'm looking at f over the interval from a to b, and I'm going to try to approximate the area there by using one of our Riemann sums that we've talked about. And again, let's just assume an arbitrary number of rectangles n. So it turns out that whether or not our named Riemann sums are guaranteed to be an over or an underestimate depends on some characteristics of our function f of x. So I'm going to go through and draw some pictures here to give us a general reasoning behind why some of these statements are true as I go along. So to begin with, I want to look at the left-hand sum. And think about comparing it to the area, we'll call that just area under our function we're talking about over the interval from a to b. If we consider the function f of x, then think about whether or not the function is known to be increasing versus decreasing. So of course, it doesn't have to be a linear function, but trending in this way. So the key feature I have here is f is increasing. And one way we can denote that is saying that this is an example where f prime of x is positive. And on the right, a decreasing function is where f prime of x is negative. So this is now going to be kind of the key characteristic. And let me actually, I'm going to get rid of that momentarily because I want to leave myself some space here for a sketch. And what I want to demonstrate here in all of these pictures is to make my life easier, just drawing a single rectangle. So if I'm looking at my generic subinterval from xk minus 1 to xk. We've already established that in drawing a left-hand sum, we are going to choose this to be our height. So I'm looking at this rectangle in comparison to the actual area under that function. And in my other picture over here, again, let's do the same general idea. I have my generic kth subinterval, and I want to again draw a general left-hand Riemann sum of just this one rectangle. And so here, the rectangle area we can consider shaded. So notice that in my picture on the left, very clearly the rectangle sits inside of the region we're looking at, and the opposite is true on my picture on the right. So in this instance over here, we see, like I said, the key feature is f is increasing. Here, f is decreasing. And again, what I'm drawing here are left-hand sums. And we see in the case that f is increasing, the smallest possible choice of the height is the leftmost edge. And so we are going to get an underestimate when we're using the left-hand sum. When f is decreasing, we find the largest possible height choice to be on the left. And so in that instance, we're going to get an overestimate when we are using the left-hand sum. Let's think about now the right-hand sum. And I'm going to do a very similar kind of picture here. So if I were to draw an arbitrary increasing function with my kth subinterval, and over here, I'll draw an arbitrary decreasing function with the same general subinterval. So in this instance, again, let's think about what it would look like. But here I want to draw the right-hand sum. for this rectangle, the right-hand sum would choose that height. Consequently, we're considering this shaded area. And on this picture, oh, nope, that's the left-hand sum. On this picture, I am going to choose this height. And we consider this area. So just like above, the distinguishing feature between these two is, in this instance, f is increasing. In this one, f is decreasing. But using a right-hand sum, we see the opposite effect. So when f is increasing, the right-hand edge gives me the largest possible value for the height. So we get an overestimate. And the opposite is true when f is decreasing. So again, these are when we're looking at the right-hand sum. So to summarize, left and right-hand sums, what we're looking at is whether or not the function itself is increasing or decreasing in terms of determining over versus underestimate. Now, let's move on to midpoint and trapezoid rule. And I'm actually going to do trapezoid rule first because it's a little bit easier to visualize that. I would say the midpoint is probably the hardest. So thinking about the trapezoid rule, it turns out that it has nothing to do with increasing versus decreasing. And in fact, if I had used the linear functions I had up here, the trapezoid rule would give me the exact true area under the curve. So I want to draw something that has some bendiness so we can think about some concavity. So let's first consider a generic function f of x that's concave up. And then I want to consider one that is concave down. Now, I have chosen to draw an increasing function. It turns out that if I had drawn decreasing functions, same result would be true in my pictures. So don't pay attention to that characteristic. Now, what I'd like to be able to draw is, again, what would happen if I were to use the trapezoid rule. And remember at the end of the last video, I pointed out there were two ways we could draw that. I'm going to use the second method where we talked about drawing a trapezoid that has area equivalent to the rectangle we described. So the way we got that trapezoid was we basically drew the lines, the secant line that connected these 2 points. And so the trapezoid rule, right, would involve looking at this area of this trapezoid. And over here, we can do a similar thing and look at the area of this trapezoid. And because the trapezoid involves that straight line, we can really see how the concavity here has that effect of when we have an over versus an underestimate, because we're basically pulling it either beneath that line or above that line. And again, you could envision doing these same pictures for decreasing functions, and note that the concavity is really what's affecting this. So what we see here is f is concave up, and this illustrates that the trapezoid rule is an overestimate. Again, there's more area under that trapezoid than under that curve. Here we see f is concave down, and we've illustrated that we get an underestimate when we find the area under the trapezoid. And so the final named Riemann sum we looked at was the midpoint sum. And like I said, this one's a little bit harder to visualize, and it turns out that the more concave I draw a function, the more easily we'll be able to see over versus under. So just like the last one, it doesn't matter if it's increasing or decreasing. Just arbitrarily, I'm going to draw increasing functions. And so let's consider something that's really concave up, and then really concave down. And again, we're going to look at the kth subinterval. In both graphs. So for the midpoint, remember that we want to look for the middle x value and consider where that intersects when I plug that into the function f. And up here, we're going to do something similar. Now, it can be hard to see here, but I want to point out, maybe I'll use green. Both of these rectangles demonstrate kind of a surplus and a deficit in terms of approximating this area. So I want to point out in each picture in green, I'll show the area that the rectangle has that is extra. Oops. This here. I seem to have lost this. And in, let's say in blue, I'll put the area that the rectangle is missing that's under the curve. Right here. And so the more extreme you draw the concavity, the easier it will be to distinguish between these to kind of see which area is larger, the green or the blue. But it turns out that what we can see here, when f is concave up, there is more blue area than there is green. So this rectangle is missing more area than it has extra. And so this is going to provide an underestimate of the true area. In this instance, there's more green or extra area under the rectangle than there is blue. And this is when we have a concave down function. Does not matter if it's increasing or decreasing. And the reason we know that we didn't just get lucky with our picture is think about what the second derivative tells us here. So in this picture here, f double prime is positive because the second derivative is the first derivative of f prime. This means f prime is increasing. So as I jump from xk minus 1 to the halfway point, the amount that I rise is now smaller than the amount that I rise as I jump from the halfway point to xk. So that's going to make up for, or explain why we have more area on the blue side. Over in this picture, we know that the second derivative is negative, and consequently that means the first derivative is decreasing. So when I do a similar analysis and look at jumping from xk minus 1 to the halfway point, we're going to have a steeper rise in y values than we would in jumping from the halfway point to xk and looking at the rise there. Okay, so now we see, kind of taking a step back, we've looked through and determined what characteristics of f lead to either an over or an underestimate in these named situations. What I do want to make sure to point out is that when I'm writing this, I'm assuming that those characteristics are true for the entire interval. So if a function switches from increasing to decreasing, you can't make a definitive statement without looking at it on a case-by-case basis as to whether the left or the right will be an over or an underestimate. Same thing goes if it switches concavity over the interval of interest. All of a sudden we have to be a lot more careful. So these are statements if you can say that it's always increasing or decreasing or always concave up or concave down. So what I'd like to finish with here is just a brief example, putting this into practice. So maybe I'll, zoom in a little bit here. So let's assume that what we're going to look at is we want to approximate the area under sine of x over the interval from 0 to pi over 2. So the first question I want to ask here, or demonstrate, is we want to rank left-hand sum with 5 rectangles, right-hand sum with 5 rectangles, midpoint sum with 5, trapezoid rule with 5, and finally the true area. And so we're referring to the area described above, and I could find each of these 4 named Riemann sums with 5 rectangles. That would give us some number, and we could compare it to the true area. So let's rank these from, say, smallest to largest. So what this comes down to is what we just talked about in terms of the features of f. So I need to consider whether on this interval f is increasing or decreasing, and also whether it's concave up or concave down. So if we were to find f prime of x, the first derivative of sine is cosine of x. And of course, that changes from increasing to decreasing, but we only care about this interval. So on that interval, if you think about the graph of cosine, that is actually going to be positive. And so that means that we're considering an increasing function. So what we know right away is that the left-hand sum is smaller than the true area, and the right-hand sum is larger. So from that alone, I can at least figure out how those 3 things relate to one another. To bring in the midpoint sum and the trapezoid rule, we need to consider the concavity. So the second derivative is now minus sine of x. And again, if I want to think about whether that is positive or negative on the interval at hand, it's negative on the interval from 0 to pi over 2. So now we know that the function is concave down on that interval. So if you look back at what we established before, if it's concave down, the trapezoid rule underestimates the true area, and the midpoint sum overestimates the true area. So the last thing I have to do is now figure out how to kind of weave these things all together. So we know that the true area here is in the middle, and we're considering these different over and underestimates. So if you think about the fact that this is increasing, so we said it's increasing and it's concave down. So I could kind of look at this last picture here. When you have an increasing function, we know that looking at this picture here, the left-hand sum and, sorry, that's not the picture. We want to look at concave down. So scratch that. If I instead focus on this one, what we want to consider is that what we're seeing here is the midpoint sum, for instance, would be an overestimate, and so would the right-hand sum. But in terms of which of those is larger, notice that in this picture here, I've drawn, for instance, the midpoint rectangle. If I wanted to go back and draw the right-hand rectangle, I would choose this height over here. So if the function's increasing, then it would always be the case that the largest possible height I could choose would come from the right edge, meaning that the right-hand rectangle is bigger than the midpoint rectangle because I can go even higher on the function to grab that. We can do a similar analysis with the function with a left-hand sum versus a trapezoid rule, which one is actually smaller in this case. And we're looking at the fact that the most extreme in terms of the smallest height is going to be the leftmost edge. So putting that all together, what we would end up with is the true area in the middle. On the one side, we have the trapezoid rule being a slightly better underestimate in some sense than the left hand. And then on the other side, the midpoint sum is going to be a better overestimate. than the right-hand sum. And then the last question here, so let's see, I numbered that 1, and so this will be 2. Now that we've established that the left-hand sum is an underestimate, the question I want to ask here is, how can I make a comparison between two left-hand sums? So we've seen how to compare different Riemann sums. So this is going to combine a couple things. In the last video, we said that more rectangles equals better approximation. So we know that the left-hand sum with 10 rectangles is a better approximation. What we need to figure out is, how does that translate to larger or smaller here? Well, in this case, both are underestimates. Of the true answer. So if you have two underestimates and we're saying that one of them is a better approximation, you want to think about which one would be closer to the true answer. So if they're both smaller, the better approximation should be larger. So putting that together, I can say that the left-hand sum with 10 rectangles would have to be larger than that with 5 rectangles. So now we're starting to see how we could rank order within one Riemann sum, how the effect of the number of rectangles is going to come into play.